The human brain is the most complex structure known to humankind. It is responsible for our thoughts, emotions, memories, and experiences. But how does it work? Classical neuroscience has made significant strides in understanding the brain's intricate workings. Yet some aspects of consciousness and cognition remain shrouded in mystery. What if the strange world of quantum mechanics plays a role? The idea that the brain operates on quantum principles is a compelling and controversial one. This hypothesis proposes that quantum phenomena, such as superposition and entanglement, are not confined to the subatomic world. Instead, they might be harnessed by our brains to achieve extraordinary feats of information processing. This is not to say that classical neuroscience is incorrect. Rather, the quantum brain hypothesis suggests a deeper level of operation. It proposes that quantum mechanics might underpin some of the brain's most enigmatic functions. These include consciousness, intuition, and creativity. The prospect of quantum phenomena occurring within the warm, wet environment of the brain is met with skepticism from some scientists. The delicate nature of quantum states, easily disrupted by their surroundings, raises doubts about their viability in such a chaotic environment. However, the potential explanatory power of the quantum brain hypothesis is difficult to ignore. It offers tantalizing possibilities for unraveling the deepest mysteries of the mind. One of the most bizarre aspects of quantum mechanics is the concept of superposition. This principle states that a quantum system can exist in multiple states simultaneously until measured. Imagine a coin spinning in the air, neither heads nor tails until it lands. This is analogous to a quantum particle existing in multiple states at once. Could our brains utilize superposition for parallel processing? The hypothesis suggests that neurons, the brain's fundamental computational units, might not be limited to binary on or off states. Instead, they could exist in a superposition of states, allowing them to process vast amounts of information simultaneously. This parallel processing capability could explain the brain's remarkable efficiency. It can outperform even the most powerful supercomputers in tasks like pattern recognition and decision-making. If neurons can explore multiple computational pathways simultaneously, the brain's processing power could far exceed what we currently believe possible. However, the idea of neurons existing in superposition is not without its challenges. The brain is a noisy and chaotic environment, and maintaining the delicate superposition states within neurons would be a remarkable feat. Further research is needed to determine if the conditions within neurons are conducive to sustaining such quantum phenomena. Entanglement, often dubbed spooky action at a distance by Einstein, is another perplexing phenomenon in the quantum world. It occurs when two or more particles become linked, even across vast distances. They share the same fate, and measuring the state of one instantly determines the state of the others. Could entanglement be the key to understanding how different parts of the brain communicate so rapidly? The brain is a highly interconnected network, and efficient communication between different regions is crucial for its function. If neurons are entangled, they could exchange information instantaneously, regardless of their physical separation. This instantaneous communication, unconstrained by the speed limits of classical physics, could explain the brain's remarkable ability to process information and generate coordinated responses in real time. Imagine the implications for our understanding of consciousness, where different brain regions seamlessly integrate information to form a unified experience. However, maintaining entanglement over long distances within the brain is a formidable challenge. The warm, wet environment is rife with interactions that can disrupt the delicate entangled states. Further investigation is needed to determine if entanglement can persist long enough to play a significant role in brain function. Section 4. Quantum tunneling, leaping synaptic gaps. Quantum tunneling is a phenomenon where particles can pass through energy barriers that classical physics deems insurmountable. Imagine a ball spontaneously appearing on the other side of a wall without breaking it down. This counterintuitive behavior is possible in the quantum realm. Could quantum tunneling be happening in our brains? Synapses, the junctions between neurons, are crucial for transmitting signals throughout the brain. When an electrical signal reaches the end of a neuron, it triggers the release of neurotransmitters, chemical messengers that cross the synaptic gap and bind to receptors on the next neuron. The quantum brain hypothesis suggests that neurotransmitters might not need to physically cross the synaptic gap. Instead, they could tunnel through the energy barrier, leading to faster and more efficient signal transmission. This could have implications for the speed and efficiency of information processing in the brain. However, the energy barriers in synapses are relatively large compared to those typically encountered in quantum tunneling experiments. Whether such tunneling events occur with sufficient frequency to impact synaptic transmission remains to be seen. Section 5. Quantum coherence, the symphony of thought. In the quantum world, coherence refers to a state where multiple particles act in unison, their wave-like properties synchronized. This synchronized behavior allows for interference patterns and collective behavior not observed in classical systems. Think of a choir singing in perfect harmony, their voices blending into a unified sound. Could quantum coherence be at play in the brain? The hypothesis suggests that groups of neurons might exhibit coherent behavior, their electrical activities synchronized by underlying quantum phenomena. This neuronal synchrony is known to play a role in various cognitive functions, including perception, attention, and memory. If quantum coherence underpins neuronal synchrony, it could have profound implications for our understanding of how the brain processes information. It could explain the brain's extraordinary ability to integrate information from different sensory modalities, forming a cohesive and unified perception of the world. However, maintaining coherence in the brain, a warm and noisy environment, is a considerable challenge. Decoherence, the loss of coherence due to interactions with the environment, is a major obstacle to realizing the full potential of quantum computation. Whether the brain has evolved mechanisms to preserve coherence for biologically relevant timescales remains an open question. Section 6. Quantum error correction, preserving our memories. Quantum systems are extremely fragile and prone to errors caused by interactions with their environment. To build reliable quantum computers, researchers are actively developing error correction techniques to protect delicate quantum information. Could our brains have evolved sophisticated error correction mechanisms to protect quantum information? Memory is a fundamental aspect of cognition, and the brain's ability to store and retrieve vast amounts of information is remarkable. If quantum phenomena are involved in memory storage, error correction would be crucial for maintaining the integrity of stored information. The hypothesis suggests that biological systems might have evolved ways to exploit quantum error correction to enhance memory capacity and fidelity. This could explain the brain's robustness and its ability to function reliably despite the constant bombardment of noise and interference. However, the specific mechanisms by which the brain might implement quantum error correction remain unknown. Identifying these mechanisms would be a significant step towards understanding the role of quantum phenomena in memory and other cognitive functions.